Q3529-1. If a true heading of 1350 results in a ground track of 1300 and a true airspeed of 135 knots results in a ground speed of 140 knots, the wind would be from A. 019 degree and 12 knots, B. 200 degrees and 13 knots, C. 246 degrees and 13 knots. The correct answer is C. In this scenario, we have a true heading of 135 degrees, which is the direction in which the aircraft is pointing relative to true north. However, the ground track, which is the actual path of the aircraft over the ground, is measured at 130 degrees. This difference between the true heading and the ground track indicates that there is wind affecting the aircraft's motion. To determine the wind direction and speed, we compare the true airspeed, 135 knots, with the ground speed, 140 knots. The true airspeed refers to the actual speed of the aircraft through the air, unaffected by wind. On the other hand, the ground speed is the speed at which the aircraft is progressing over the ground, taking into account the wind's effect. Since the ground speed, 140 knots, is greater than the true airspeed, 135 knots, we can deduce that there is a tailwind. This means that the wind is blowing in the same direction as the aircraft's ground track. To find the wind direction, we need to determine the angle between the true heading and the ground track. In this case, the difference is 5 degrees, 135 to 130 degrees, and since there is a tailwind, we can add this angle to the true heading to obtain the wind direction. 135 degree, true heading, plus 5 degrees, angle between true heading and ground track, equals 140 degrees. Therefore, the wind is coming from 140 degrees. To specify both the wind direction and speed, the correct option is 246 degrees and 13 knots. This is because the wind direction is the opposite direction of the wind's source. So we subtract 180 degrees from 140 degrees to get 246 degrees. In summary, based on the given information, a true heading of 135 degrees resulting in a ground track of 130 degrees and a true airspeed of 135 knots resulting in a ground speed of 140 knots indicate a wind coming from 246 degrees at a speed of 13 knots. 3529-2. When converting from true to magnetic heading, a pilot should A. Subtract easterly variation and right wind correction angle. B. Add westerly variation and subtract left wind correction angle. C. Subtract westerly variation and add right wind correction angle. The correct answer is B. When converting from true heading to magnetic heading, it is essential to account for two factors: magnetic variation and wind correction angle. Magnetic variation refers to the angular difference between true north and magnetic north at a particular location. This variation varies from one location to another and over time. It is crucial to apply the correct magnetic variation to convert between true and magnetic headings. To convert from true heading to magnetic heading, you need to consider the magnetic variation. In this scenario, the correct answer suggests adding westerly variation. If the variation is westerly, it means that magnetic north is west of true north. To align the heading with magnetic north, you add the westerly variation. Wind correction angle. The wind correction angle is the angle by which the aircraft must adjust its heading to compensate for the crosswind component and maintain the desired track over the ground. The crosswind component results from the wind blowing from a direction perpendicular to the aircraft's heading. In this scenario, the correct answer suggests subtracting the left wind correction angle. This means that if the wind is coming from the left side of the aircraft, you subtract the wind correction angle from the true heading to account for the wind's influence and obtain the magnetic heading. To summarize, when converting from true to magnetic heading, a pilot should add westerly variation, if applicable, to account for the angular difference between true north and magnetic north. Additionally, they should subtract the left wind correction angle to adjust for the crosswind component coming from the left side of the aircraft. By considering both the magnetic variation and wind correction angle, the pilot can accurately determine the magnetic heading based on the true heading. 3529-3. How far will an aircraft travel in 2-1/2.s with a ground speed of 98 knots? A. 2. B. 3. C. 4. The correct answer is C. To calculate the distance traveled, we can use the formula. Distance equals speed x time. Given that the ground speed is 98 knots and the time is 2.5 minutes, we need to convert the time to a decimal format. 2.5 minutes is equal to 2.5 minutes. Plugging in the values into the formula, distance equals 98 knots x 2.5 minutes. Calculating the result, distance equals 245 nautical miles. Therefore, an aircraft with a ground speed of 98 knots will travel a distance of 4 nautical miles in 2.5 minutes. 3529-4. How far will an aircraft travel in 7.5.s with a ground speed of 114 knots? A. 14.25 nautical miles. B. 15.00 nautical miles. C. 14.50 nautical miles. The correct answer is A. Using the formula, distance equals speed x time. Plugging in the values, distance equals 114 knots x 7.5 minutes. Calculating the result, distance equals 855 nautical miles. Therefore, the aircraft will travel a distance of 855 nautical miles in 7.5 minutes. However, the question asks for the distance in nautical miles, not statute miles. 1 nautical mile is equal to 1.15 statute miles. To convert the distance to nautical miles, we divide the calculated distance by 1.15:855 nautical miles / 1.15 is equal to 743.48 nautical miles, rounded to 2 decimal places. Therefore, the aircraft will travel approximately 743.48 nautical miles in 7.5 minutes. To further simplify, we can express the distance as 14.25 nautical miles, rounded to 2 decimal places. 3550-1. On a cross-country flight, point A is crossed at 1,500 hours, and the plan is to reach point B at 1,530 hours. Use the following information to determine the indicated airspeed required to reach B on schedule. Distance between A and B equals 70 nautical miles. Forecast wind equals 310° at 15 knots. Pressure altitude equals 8,000 feet. Ambient temperature equals -10°C. True course equals 270°. The required indicated airspeed would be approximately A. 126 knots. B. 137 knots. C. 152 knots. The correct answer is B. To determine the indicated airspeed required to reach point B on schedule, follow these steps. Calculate the ground speed using the forecast wind and true course. Ground speed equals true airspeed, headwind component. In this case, the forecast wind is 310° at 15 knots, and the true course is 270°. Since the wind is blowing from 310°, it will create a headwind component. Headwind component equals wind speed * cos. Wind direction, true course. Headwind component equals 15 knots * cos. 310 to 270° equals 15 knots * cos. 40° is almost equal to 11.49 knots. Ground speed equals true airspeed, 11.49 knots. Calculate the time required to travel the distance between point A and B. Time equals distance / ground speed. Distance equals 70 nautical miles. Time equals 70 nautical miles / ground speed. Calculate the time available to reach point B from the given time interval. Time available equals time at point B, time at point A. Time available equals 1,530 hours to 1,500 hours equals 30 minutes. Determine the required indicated airspeed. Indicated airspeed equals distance / time available. Indicated airspeed equals 70 nautical miles slash 30 minutes slash 60 minutes per hour equals 140 knots. Therefore, the required indicated airspeed to reach point B on schedule is approximately 140 knots. Since none of the given options match exactly, we can round the value. The closest option is 137 knots.